Why, hello, lovely humans! Welcome to part 3 of Fourier series. Yeah! Alright, so we have finally made it to the point where we are ready to do an actual example. Look at that. Okay, so in the previous part, in part 2, we looked at how do we find the coefficients of our Fourier series. Pretty important, because otherwise we just have a general formula that doesn't actually apply to any given situation. So, okay, we talked a lot about sound, but sound waves are a little tricky. So let's start with something even more simple, but still super useful, and it crops up all the time in the real world, especially if you work with electronics. So let's say that we are given, oops, I guess this can be a straight line. We are given a periodic voltage pulse that looks like this, where we have on, and then it's off. We'll say that this is pi for the sake of having a periodic function with a period of 2 pi. So I'm going to write that in the corner. So our period is 2 pi. So then at 2 pi, it starts again, and then it goes until 3 pi. And then likewise, we can also go back and we can say that at negative pi, we have our signal going like boop all the way to negative 2 pi, and this is 0. Okay, so then this vertical axis is what we will call f of x, and this point right here is 1. So when you are creating a Fourier series, maybe if you're lucky, you're given a picture like this, because as they say, a picture is worth 1,000 words, or in our case, a picture is worth 1,000 equations, or maybe at least one equation. Okay, so you are most likely given the function in math speak or whatever. And so in this case, that was a hilariously bad bracket. In this case, our function is represented like this. Let's try this again. Okay, there we go. So our function is 0 for negative pi less than x less than 0, and 1 for 0 less than x less than pi. And since we are told that it repeats over time, you basically take this function and you infer these and onward. And so in this case, this is where you're like, oh, okay, this function would be really, really difficult to implement in a coding program. And so something that would be a little bit easier would be to use sine and cosine, especially if you're working in something like R, the statistical program, or if you have Python, you can import these math functions and just use sine and cosine without having to define them. Woo, makes our lives easier. Okay. So now that we are given this function, if you are not given a picture, I would always recommend drawing a picture. So I like to talk about how understanding is critical in mathematics. And a lot of this is coming from having done physics, because to be honest, I didn't memorize a ton of equations. Once you have done the equations enough times, they get burned into your brain. But when we're given, most of the time on a test, we're given the equations, but that doesn't necessarily mean that it's helpful. You have to understand what you're doing. And I can't tell you the number of times where I sat and drew a picture and that was the thing that made my brain click. So if you're visual like me, definitely draw a picture, and even if you're not, still draw a picture. Okay, so let's find a of n first. So, yeah, I'm not going to rewrite the general equation because we're just going to apply it here as I look at my notes down below me. But if you want to, I would recommend when you watch part 2 that you actually write down those equations, or at least have your notebook handy, or your math textbook. Okay, so this is the equation for a of n, which are the cosine terms. So again, we're going from negative pi to pi. F of x. So I'm like, I'm not going to rewrite them. I'm going to rewrite them. Cosine of nx dx. Okay, so basically now what we want to do is we want to break apart this integral into these two chunks. So you can see that we have one piece of our integral is 0, so from negative pi to 0, and the other piece of our integral is 1 from 0 to pi. Okay, and that looks like this. I'm going to pull out the 1 over pi, and so our first integral is going to go from negative pi to 0, and we look and see what the value of f of x is between this interval, and it's 0. Ha, well, that's easy. So 0 times cosine of nx dx. Ha, easy peasy. And then the second one goes from 0 to pi, and this is 1 times cosine of nx dx. And then I have a bracket that is almost off the page there. Okay, so cool. All right, so now this is actually pretty straightforward. I'm going to double check my notes, make sure I don't mess anything up. Okay, so this goes to 0, easy peasy, and we are left with 1 over pi, 0 to pi, cosine of nx dx. That's not so bad. We can do this. Okay, 1 over pi, the integral of cosine is sine, so we get, but we have a factor of n in here, so we have to divide by n. So we're going to multiply by 1 over n, and then we get sine of nx from 0 to pi. Okay, yay! And now I'm running out of space. Actually, I can write below here. Okay, so now I have 1 over n pi sine of n pi minus sine of 0. Okay, so let me think about the unit circle. So sine of 0 is 0, and sine of any multiple of pi is also 0. Ha ha ha! Look at that! Wait a second. Hold on. I think I messed that up. Oh, okay. I got ahead of myself here. Okay, so, I'm gonna back up a little bit. Yeah, okay. So, this is where we have to ask, what are the possible values of n? Well, n could be anything from 0 onward. So if we have cosine of 0, that's actually going to turn our integral into something very different. So for n equals 0, we have 1 over pi, the integral of 0 to pi. Cosine of 0 is actually 1, so we get dx. And then this is going to be 1 over pi times, this is just going to be x from 0 to pi equals 1 over pi, pi minus 0, so we're just going to get pi, and this equals 1. Ha! Look at that. Pretty cool, right? Okay, but now, all of a sudden, I'm going to leave this last line and erase this. And so for n not equal to 0, that's when we have to actually evaluate this integral. So for n not equal 0, we have an equals 1 over pi, 0 to pi. I can do that. So the integral, like we just did before, is 1 over n sine of nx from 0 to pi. And so this is what goes to 0. So you get, again, 1 over pi, 1 over n pi times 0 equals 0. Okay, so for n equals 0, or a0, you get 1. Cool. Okay, so I'm going to write that up here. So a0 equals 1. Ta-da! That's pretty great, right? Most of the coefficients in the cosine term went to 0, which, when you know the picture of cosine, how it looks like, that makes sense, right? Because sine starts at 0 and, wait, is that right? Yeah, sine starts at 0 and goes like this. So this function, you could say, has mostly sine in it, whereas cosine is going to come down like this. And it makes sense to have the first term be 1 because you are starting at 1. Okay, so now we do sine. The the sine terms, or the b terms, yay! So 2bn equals 1 over pi negative pi to pi of f of x times sine nx dx. And again, we have to break this apart into the two pieces. So we have 1 over pi times the integral from negative pi to 0, which is 0 times sine nx, plus 0 to pi, which is just going to be 1 times sine n, oh my gosh, I forgot the dx, and x dx. Okay, this goes to 0, and I am left with 1 over pi. I keep writing down, it's funny. 1 over pi, 0 to pi of sine nx dx. And again, I have to break it into two pieces. So let me just double check. Yeah, okay. So for n equals 0, we have sine of 0 is 0. So our integral just equals 0. So we have 1 over pi, integral 0 to pi, sine of 0 dx. This goes to 0. And for n not equal to 0, can you all see that? I might be writing a little small. Okay, let's move up a little bit. Okay. So, oops. Actually, I'll do this. So bn not equal to 0 equals 1 over pi integral from 0 to pi of sine nx dx. Okay, so this one, again, pretty straightforward. You have a factor of 1 over pi, the n comes out, you divide by n, and you have a negative, whoops, that's not a negative cosine nx. And then that is all from 0 to pi. Okay, and I'm going to erase that because we don't need it anymore. Just remember in your heads that the first term in the sine coefficients went to 0. Okay, so now we have 1 over n pi, and we need to evaluate this. So I'm going to bring the negative out just to make my life a little bit easier. And I have cosine of n pi minus cosine of 0. Okay, so let's hold off on this for a sec. This goes to 1. And so now I have negative 1 over n pi cosine of n pi. Okay, so let's talk about this. And I'm going to draw the unit circle to help us visualize. So the unit circle is a circle with a radius 1, where this is x and this is y. And so cosine is adjacent over hypotenuse, so that means cosine corresponds to the x-axis and sine corresponds to the y-axis. So cosine of 0 is here, so hence cosine equals 1. Cosine of pi is over here, so this is going to be negative 1. But then we go back around. So for n equals 0, we get 1. For n equals 1, we get negative 1. For n equals 2, we get a positive 1. For n equals 3, we're back over here, and we get a negative 1. And you keep going around and around the circle. It's a periodic function. So you alternate between 1 and negative 1. The even numbers of n give you a positive 1. The negative numbers of n give you a negative 1. Okay, so that's a little wonky. How the heck do we represent that? It's not so bad, actually. So a really cool trick is to say, okay, well, it's just negative 1 to the n. And you can double check this. I would challenge you to do this on your own, where if you have n to the 0, you get 1. If you have n to the 1, you get negative 1. Check. N squared, or n equals 2, you get negative 1 squared. That's going to give you a positive 1. If you have n equals 3, this is going to give you a negative 1, just like you would expect. So, huzzah, it works. So, but we can't forget this other term here. That's super important. So we are going to subtract a 1. Okay, so this is really interesting because this tells us that when we have a positive 1 here. And remember, even numbers of n, even n, this is going to be a positive 1, and this whole thing is going to go to 0. So b of n equals 0. But for odd n, b of n equals, oh my gosh, running out of space again. Here, we'll do this up here. I'll keep this. So b even n equals 0. But b odd n equals -1 over n pi times, this is going to give me a -1. -1 minus 1 is -2. So this is going to give me a positive 2 over n pi. Boom! And let me just double check that this is right. Yes. All right. So now we have b odd n equals 2 over n pi. Rad, right? So now we can write the Fourier series. The expanded, the Fourier series that expands this function in terms of sines and cosines. So now our function is not discontinuous. Yay! Now we can write it as a series of sines and cosines, which means we can do a lot more cool things with it. So the first term, a naught is 1. So remember we have that 1/2, so we have a 1/2 times 1 in there. And now we just wiped out all of the cosine terms, so those all went to 0. And the only terms we have left are for odd numbers of n. So that would be a1, which is going to be for n equals 1, so it's going to be 2 over pi times sine of x. And the even ones go to 0, so we skip that. And so now we have 2 over 3 pi for sine of 3x plus 2 over 5 pi for sine 5x plus etc. Pretty rad, right? That's it. This is our Fourier series expansion of this discontinuous function. And the last thing that I want to note is that the magnitude, or how big each of these coefficients are, determines how much they come into play. So for example, the reason why we can say ... we don't really care, is because as these fractions get smaller and smaller, the contribution of these subsequent sign terms also gets smaller and smaller. So what this means practically, for example, going back to sound, because it's something that's near and dear to my heart, what this means is that a higher quality audio signal would have more of these sign terms, to the point at which the frequency gets so high that the human ear can't hear that. It is kind of interesting though to note when I listen to records for the first time, as a child of the 90s, our jam was CDs, and so I actually heard digital music, CDs, before I heard records, which is actually analog. So the sound wave literally gets imprinted on the record. So it's a really close sound to what you would actually hear live. And I remember hearing a record for the first time and I was like, oh my gosh, this sounds like it's live. And especially with early digital music, they would truncate these Fourier series pretty early on because space was an issue. We didn't have a lot of memory to store all of these terms, but as space has increased, audio files can be much larger, and so that means that we can include a lot more of these Fourier terms. So that's literally what it means to have more and more Fourier terms. And again, at a certain point, the human ear can't hear, so you don't actually have to include an infinite number of terms. We don't have an infinite number of storage space, but you would include enough up to a point at which the human ear can't make a difference. And then maybe you get close to the way a record sounds. Pretty cool, right? All right. So please let me know if you have any questions about the procedure here, or if you're curious how you might apply this to a different type of function, different type of periodic function. Like I mentioned, we will get to Fourier transforms. I have a couple of other videos I want to do in the meantime, but eventually I'll come back to Fourier transforms, and we will look at non-periodic functions for that. So again, please let me know if there are any math topics that you're super curious about, and I'm also taking math myths. Ooh! So what are the myths that you've heard that have to do with mathematics, and let's tackle them together. Thank you very much for watching, and I'll see you next time. Bye!